Hey everyone. So thanks for having me here to talk today. So I'm going to be talking about a Morita-type theorem for quotient categories. So that's a lot of words, but not a lot of meaning so far. So let's talk about what Morita's theorem is. Okay. So a few people over the course of the conference have mentioned abelian categories, but they haven't really gone into what they are. So I'm going to continue that trend. We can just think about them essentially as being the category of modules over a ring. Okay, so a few examples. Obviously, the category of modules over a ring. If we have an abelian category A, we can look at the cochain complexes in A, and that again forms an abelian category. And also, if we have a Noetherian ring, the category of finitely generated modules over this ring is abelian. Okay, so most of the time we can think of abelian categories as being modules over a ring, but not all of them actually are. So our third example that we just gave is one of these cases. So the category of modules over a ring is always complete, but an infinite product of copies of a finitely generated module is no longer finitely generated. So this is an example of an abelian category that's actually not equivalent to the category of modules over any ring. Okay, so this is the question that Morita's theorem answers for us. It lets us know when an abelian category is actually equivalent to the modules over some ring. Okay, so first thing we want to do is try and find a natural way to get a functor from our abelian category into the modules over some ring. And this actually arises naturally through looking at endomorphisms of objects. So being an abelian category, our set of endomorphisms has a natural group structure, but actually it really naturally has a ring structure where our multiplication is given by a composition of endomorphisms. Okay, and with this ring structure, the group of morphisms from our object X to any other object Y naturally becomes a right lambda module. And then this in turn extends our Hom functor from a functor from A to set to a functor from our category A to the modules over this ring lambda. So now we want to know, when is this functor an equivalence of categories? So the key insight is that we want to look for an object in our category that behaves similarly to the ring itself when you consider it as a module over itself, actually. So what do we actually need? So we know that the ring is finitely generated. So this may be a bit more highbrow take on finite generation. So we say that for any directed set of subobjects or ideals you can think of, these Mi, whose sum is actually equal to R, there's some index J such that the object Mj is actually equal to R. Okay. Secondly, we know that R is a generator. So I'm sure everyone's more familiar with the definition that it means that the Hom functor is faithful. But actually it's equivalent to this definition that every R module is a quotient of a coproduct of copies of R. And this is just the familiar fact that we all know that every R module is a quotient of a free module. Okay. Next, we know that the module R is projective. So this Hom functor is always left exact. But when we consider the Hom functor of R, it actually also preserves surjections. Okay. So any object satisfying these three properties, we call a progenerator. And lastly, we always say the object's compact if this Hom functor commutes with filtered colimits, or really we only care about it commuting with direct sums. All right, so these are all the conditions that we actually need. And then we have this theorem of Morita that says that if we have an abelian category A with a compact progenerator P, then this Hom functor from P to blank defines an equivalence of categories between A and the category of modules over the endomorphism ring of our progenerator. Okay. And this is the theorem that we want to emulate for a different type of abelian category. So instead of looking at when we're equivalent with ModR, we're going to look with when we're equivalent to a quotient category. Okay, so let's talk about quotient categories now. So I'm going to start with a bit of a motivating example as to where these quotient categories come from. So let's look at our extension of scalars functor that we have tensoring over Z by Q. And let's just restrict it for the moment to finitely generated abelian groups to finite dimensional rational vector spaces. Okay, so this functor, it's exact, it's full, and it's essentially surjective, but it's not faithful. Okay, so we can see that pretty easily. So if we take any finite abelian groups, so Z mod 2, Z mod 17, Z mod whatever your favorite integer is, we have the image of these groups under this extension of scalars functor is just isomorphic to the zero vector space, the trivial space. But for any more non-finite abelian group, so if we have some free component, so say Z squared, for example, it's not going to be isomorphic to zero. So Z squared, it becomes a two-dimensional rational vector space. So in general, any two abelian groups are isomorphic, well, the images under this functor are isomorphic, if and only if they have the same rank. Okay, so very imprecisely, we can think about rational vector spaces being like abelian groups mod out by torsion. So this is what we want to make precise by introducing quotient categories. So there's two things that we want to capture from that previous example. So the two important things are that the inclusion of the torsion abelian groups into the abelian groups is exact and fully faithful. And secondly, that Q is flat over Z, and tensoring any torsion abelian group with Q gives you the zero vector space. Okay, so let's have a look at this first condition. So we're going to define our subcategories that we want to quotient out by now. So our analog of the torsion abelian groups from that example. So we say that a full subcategory of A is SIR if for every short exact sequence in A, we have that our middle object is in T, if and only if the two outer ones are as well. Okay, so this means that T is closed under sub-objects, quotient objects, and extensions, right? And this exactly tells us that the inclusion of this full subcategory into A is exact and fully faithful. So this ticks off our first box we wanted to, first condition we wanted. So now let's go on to the second. So we know that Q is flat, so this tensor functor is exact, and that it sends every torsion abelian group to zero. Okay, so we're gonna so just define our analog of rational vector spaces. So what our quotient category by this subcategory will be. We're going to do it in a bit of a cheap way. We're just going to say that our quotient exists precisely of what we want. So we want an abelian category, which we call A on T. And we want an exact functor from A to A on T, such that the image of every object in our subcategory is isomorphic to the zero object in our quotient. Okay, and we want it to be universal with respect to this. So if we have another category B, an exact functor that satisfies these properties, then we get a unique functor from our quotient to this B, making the appropriate triangle commute. Okay, and then pretty cheaply, this satisfies everything that we want. So we can tick off our second object. So these are our quotient categories that we're going to be working with. So far, I've just defined it in terms of a universal property. We don't actually know whether it exists or not. So I'll flash up the construction here. I'm not going to talk about it at all because it's not really important. It just matters that they do exist. Okay. So now we know what quotient categories are. The last thing I'm going to do is introduce the type of category that we're going to be taking the quotient of. And then we can get on to our Morita-type theorem for these categories. So for a bit of motivation of where these categories come from, we'll think about free modules over graded algebras for a second. So if you haven't played around with graded algebras before, and your intuition's just coming from regular algebras, you might not think that this is too interesting, right? Because if you have an ungraded algebra, the only rank 1 free module you have is that algebra itself. But with graded modules, we actually get countably many free modules of rank 1. We get all the shifts of this algebra that we get just by shifting the grading, okay? And using this sequence of rank 1 free modules, we can define a new algebra, which is now bigraded. So graded by 2 copies of Z. We call it A hat, or A bar, sorry. And it's just given by the direct sum of all of the morphisms between these different objects, these different rank 1 free modules. Maybe surprisingly, this new algebra is actually graded Morita equivalent to this first one. So I thought that was pretty interesting the first time I saw it. But what I thought was even more interesting is actually if we have another graded Z-graded algebra B, A and B are graded Morita equivalent if and only if this A bar and B bar are isomorphic as algebras. So it actually contains all the information about the graded module categories. Okay, so with this little example in mind, I'll go on to define an indexed algebra. So we take a directed set I and a field K, and we say an I-indexed algebra is a K-linear category C whose objects are indexed by this set I. Right? We call this an indexed algebra because from this we can define the algebra of morphisms here, just like in the previous example. And it's again an I bigraded algebra. Okay. We say we have a graded right A module. It's an abelian group graded by I, but only singularly graded. And it has a linear multiplication of this form, satisfying all your module axioms. Okay, and then this is how we denote the category of graded right A modules. Okay, and lastly, we want to work with some finiteness conditions on these algebras. So, as I mentioned earlier, sorry, the finitely generated modules over a Noetherian ring or a Noetherian algebra form an abelian category, but in fact, these two conditions are equivalent. So our algebra is Noetherian if and only if this category of finitely generated graded A modules is abelian. A lot of the time, finite generation is a bit of a strict condition. We'd prefer to work with finitely presented modules. So what do we have in this case? So this is where we get our coherent algebras. So we say an I-indexed algebra is coherent if the full subcategory of finitely presented graded A modules is abelian. Okay, and then if this is the case, we'll denote this full subcategory by co of A, and we'll call the modules coherent modules. Right? So this is the category that we're going to work with, but we want to take a quotient of it. So we need to introduce the Sur subcategory that we want to quotient out by. So what we're going to look at is bounded coherent modules. So these are all of our graded modules, graded coherent modules that have vanishing tails. So what this means is that there's some index n in our grading set I, such that for every element of our set greater than n, all of the components in that degree vanish in our module. So you can think of it as like we can go far enough along in our set, or far enough along in our graded module, and it becomes 0. Okay, and when our algebra is coherent, this subcategory is actually a Sur subcategory, so we can take its quotient. We'll call this quotient coproj. And now our question becomes, when is an abelian category equivalent to one of these coproj categories? Okay, so let's just take stock for a second. In the classical case, we wanted to know when A is equivalent to the modules over some ring, and we had to look for a progenerator. So now we want to know when A is equivalent to a coproj category, but what do we need to look for? So we've actually done the hard work already, figuring out where to go. So in the case of just a regular ungraded ring, we only have the one rank 1 free module. But in our case, we have this whole sequence of modules, like we saw earlier with the free modules over the graded ring. So now instead of looking for one object, our progenerator, we want to look for a sequence of objects in our category behaving similarly to this progenerator. So if we have a sequence of objects indexed by our directed set I in an abelian category, then we can use this sequence to define an I-indexed algebra. We call A dependent on the sequence E, and it's just given by the sum of the morphisms between the objects in the sequence. And again, with this sequence, we get a functor gamma from A to the category of graded modules over this algebra, given by the direct sum of these Hom functors. Okay, and now what we want to know is, firstly, when is this algebra coherent? And then if it's coherent, we make this gamma bar functor by composing gamma with the quotient functor. So now we have a functor from A to the coproj category of some algebra, and we want to know then when this is an equivalence. Okay, so how am I going for time? Okay, so before we had the three different conditions to be a progenerator, right? You needed to be projective. So here we have our equivalent, or our analog of being projective. I won't go too much into these conditions because it's a lot of text. But essentially, these are analogs of the three progenerator conditions that we had before. So we have projective, which is the analog of projective. We have our coherent condition, which is our analog of finite generation. But now we're working with coherent or finitely presented and coherent algebras instead of finitely generated and Noetherian algebras. And lastly, we have ampleness, which is our analog of the generator condition for a progenerator. Okay, so if a sequence satisfies all three, we just refer to it as ample. And then with these definitions, we can go on and state our Morita-type theorem. So if we have a k-linear abelian category A, and it has an ample sequence of objects, well, then the algebra associated to this sequence is coherent, and the functor gamma bar from A to the coproj category of this algebra is an equivalence. Okay, thanks for listening to my talk.
Thank you very much, Jackson.